We're living in the age of AI, and wherever you go in the Bay Area, everybody's talking about large language models. So everybody's playing with ChatGPT, Bard, Llama. What nobody's talking about is the amount of compute that is necessary to support these language models, right? So on this slide in the top right corner, I kind of put a kind of graph from Microsoft that was kind of showing the rapid growth in size of these AI models. They're roughly doubling in size every 3.5 months. On the bottom is really our kind of supply for this compute. And the gap between them needs to be closed either by throwing more chips at the problem or coming up with designs that are more specific for that specific application. You have an explosion of these domain-specific architectures that are really focused towards a set of workloads to efficiently implement those specific workloads. And Groq is just one of those domain-specific architecture, the Groq chip. But we have taken a very different approach than everybody else on the market, right? We started Groq as a software-first company. Before we even wrote a single code of RTL, we started by figuring out the software and the software compilers that are going to be necessary to map these algorithms into hardware. So on the left, you see the typical AI accelerator of today. It's the GPU. You see a large number of cores arranged in a two-dimensional array here. Each of these cores executes portion of the workload. They're non-deterministic. What I mean by that is they execute the fastest possible they can do. They all fight for resources, I/O resources, DRAM resources to solution a problem. What you also see on this slide, you see the complexity of kind of the layout. So just if you look at the floor plan, there's a lot of control logic in the GPU that's kind of managing the flow of data between these cores. But if you look at the Groq chip, what you see is a very regular structure. We've actually stripped away a lot of the dynamic control off the chip and moved it to software. So what we're left with is a very much the actual execution units, the data paths that are executing these workloads, and we have I/Os to kind of provide the data, and then we have about 3% of the silicon area devoted to control versus about 30 that you see in a typical accelerator. So what this has done, it's actually created a chip that's deterministic in nature, which means that at any point in time, we know exactly where the data is located in the chip. We know exactly what functional units are activated in a clock-by-clock basis. And this has enabled us to actually solution software much more efficiently, which is the biggest problem in today's AI accelerators. It's actually enabled the renaissance in how quickly we can compile new AI models. So this slide shows that in the first 6 quarters, for starting last year, we went from about 0 to 60 models, AI models that were compiled. But because our compiler is evolving so quickly, in a push-button approach, we were able to compile an order of magnitude more models in just 6 weeks. And just to give you a feel how long it would have taken to compile these models in a GPU-like approach where you have to kind of code in these hand-coded kernels, we estimated that you needed about 20 million person-hours to code these special kernels that are crafted to kind of solution all these models in hardware. On this slide, I show our chip, and this regular nature of the chip is really enabling us to kind of focus even our static sign-off and simplify that as well. If you look at the top and the bottom of the chip, this is where you see most of the asynchronous interfaces. These are the kind of the C2Cs, SerDes that are really driving asynchronous crossings. This is where we have focused CDC and RDC. And then the rest of the core is running on a single clock. So there is no different clock domains crossing. So here we can focus on lint and try to get the maximum benefit out of that. Now, out of lint, we have very repeated blocks. So that also streamlines how quickly we can move through static sign-off. And we have taken the same approach that was described by the Esperanto, by Raj, where we actually engage with lint very early in the flow. This is all automated, so we maintain our repositories always lint clean. So as soon as somebody makes a change in RTL, we automatically launch kind of lint and other checks to make sure that those are clean before they're checked into our golden repository. So using this approach, we've been able to really increase the speed of iteration. And we've really enjoyed the tools from the aspect of reduction in false positives. This is minimizing distraction for our logic team. We have really good FAE supports, which, let's face it, every EDA tool is going to have their bugs. It's how quickly the response is to address these bugs that makes the difference of how we pick our vendors. And then, as I mentioned, the automated lint really keeps our repositories always clean and ready to kind of tape out. So always kind of keeping the cleanest possible state of our blocks. So that's currently. What we want to see in the future is really an increase in this overlap between logic design, verification, and physical design. So we would love to see lint co-pilots or autopilots that are constantly managing as we write RTL code, so we get that feedback immediately. We would love to see suggestions of how we would fix some of these problems that are identified by lint. We would love to get even further shift left, right? So basically get the feedback on the fly. I would love to see an ability to stack logic design, design verification, and PD and compress those time to market cycles. And we can do this by making sure that the logic designers, when they're coding that RTL, feel the pain of the physical designers having to implement this in silicon. So we would love to do some light synthesis potentially and provide feedback on how wire constrained we are. Like, what's the flop to flop logic stages? Can we actually get feedback on power? Maybe suggest assertions that need to be coded into specific blocks, even implement those. So these are some ideas where you can argue you can use AI to help the next generation of AI accelerators. I think with that, I'll leave you. Thank you.